Okay, let's start our next lecture. Let me quickly review what we did last time. So we started, I even have the remains of the diagrams right here. You can see S here. So we considered the Stallings diagram and then we pulled it back. So we replaced this X, Y, Z and S with the hats. With X hat, Y hat, Z hat, S hat. And now each of these has an action. So gamma action. And gamma acts on each of these each of these terms. On Z hat, S hat. And now going back to, I mean, that was a general situation, right? These can be assumed to be complexes, not just graphs. But going back to the original problem, let's consider the case when they were graphs. So when X, Y, Z, and S were graphs, and then the universal covering of X, which is X hat here. That's a decay graph for a free group. It's a tree.
The maps are gamma equivariant?
And the maps are gamma equivariant, yeah. So all these, yeah. So and these are leafages. So this is a leafage, means that, so the picture is like this. I drew it last time. So the picture is from here to here. This is X. Leafage means that each component by this map is mapped injectively. So the components are like leaves, you can call them. The whole map doesn't have to be injective, but when you restrict it to the component, it is injective. So if I take some edge here, some edge E, say, then here take the full preimage of this. There might be an edge here that maps to it, there might be an edge here that maps to the same thing. So you take the whole fiber. And we use the fact that so gamma is free in the case of graphs, right? So that implies that it's left orderable. Is left orderable.
Just to be clear, when you say gamma action, it always means free gamma action?
Yeah, for all these, of course one can, when I will talk about submultiplicativity, which is a generalization of the question, it's a question which is more general than Hanna-Neumann conjecture. Then one might also try to consider non-free actions, but let's stick with free actions just for simplicity.
So the preimage is same as the folding number of a cover from Y to X?
Yeah, exactly. So this diagram is the pullback of this diagram. Z and S, maybe I should draw it like this. Z, S. Yeah, so the fibers, the preimages of edges here are the same as preimages of edges here. They are isomorphic sets. So gamma is free, so it's left orderable. Or in general, we just can consider. Now, that's again an indication how you can generalize a question. You could just consider a question not about a free group, but just start with a left orderable group. And then try to, and then draw a system of complexes, as I did before, consisting of these diagrams. And then try to generalize the question, but we will do it later on. So we take the preimage, this is a fiber. So put left orderable means there is an ordering on gamma. So put a gamma invariant order on the edges of X hat first. So we just pick some fundamental domain of edges in X hat. And then we spread this fundamental domain by the action of the group. You used so the set of edges is the Cartesian product of gamma with some finite set. So you put the lexicographic order on this Cartesian product. That gives you a left invariant order on the set of edges in here. And then you pull it back here and you pull it back here. And there are two ways to do it. I mean, it's pretty much the same way. Right, it's just stated in different words. One way to say it, you consider this as a fiber over as a fibration over this. In other words, for each edge, take the pre-image. So it's something like the edges in X hat times the fiber, even though the fibers might be different, so one must be a little bit more careful there. But it's something like the Cartesian product. So you put exactly the lexicographic order in the right way. It's important that the order on the edges of X hat is more important than the order on the fiber. You remember there are two lexicographic orders that you can put on the Cartesian product. So if you really want the total order on the edges of Y hat, it's important to take the right lexicographic order, meaning that the group, the edges in X hat, the order on the edges in X hat should have priority over the order on the edges in each fiber. Or you just take components. You take components of Y hat, there are these leaves, and each leaf maps injectively into X hat. So you just determine, you define the order on the edges in each component just by mapping it here and restricting the order on the edges in X hat. So we can do it just on each component. That's enough for the purposes of the proof. So gamma invariant. So then use it to induce orders on orders, either total or partial. So total or just total on each component. On each leaf, right? Component on the set of edges in Y hat, the set of edges in Z hat, and the set of edges in S hat. Since this order on the edges in X hat had priority in the definition of the order here, here, and here, that means that these three things will be consistent. So these orders are consistent in the sense that, so these are consistent in the sense that on each component, after you map it, it coincides with the order on the image. The order on each component, leaf, right? Component, again, because it maps injectively on each component of, say, S hat, coincides with the order induced by mapping this component to, say, Y hat. To, say, Y hat. So, in other words, the short way of saying this, leafages preserve order. And for the sake of notation, I might call, so one component, the image of this, so pick one component, you can think of this being a subcomplex in X hat after mapping it here. So this is what we called A, cursive A. It was this graph invariant under the subgroup A. And the action of the subgroup A on this graph, on this tree, is co-compact. The quotient is finite. And the preimage, just for the sake of notation, we could call it, say, Y hat and 1, where 1 is the trivial left coset. You remember these components corresponded to left cosets of A and gamma. So this 1 here is the left coset corresponding to the identity element. It's the trivial left coset. So more generally, if you the general component I could call y hat sub y, where y is a left coset of A in gamma. So those components are labeled by left cosets. So the components of y hat, y belongs to gamma over A. These are all components of y hat. You pick a left coset, corresponding to that left coset there is a component of y hat. Similarly for z hat, z sub z, you can call it, it's where z belongs to the left coset of gamma over B. And what are the components of s hat? The components are the intersections. If I call this map, let's call this map alpha, this is beta, then this map you might call alpha hat and beta hat. Then what are the components of s hat? They correspond to pairs of these. So you pick y and z in the Cartesian product of these two, gamma over A, Cartesian product with gamma over B. And for each such pair, you can denote s hat sub xy to be the intersection of the corresponding component. Intersection meaning that you take one component here, map them here, and then intersect.
YZ?
Oh, yeah, sorry. Yeah, YZ. YZ, and so it's alpha hat of y hat sub y intersected with, so it's a copy, it's an isomorphic copy of it, of beta z, so z hat sub z, right? So this is, and now you take the disjoint union of all such, over all pairs. So for each pair you make a copy, and then take the disjoint union of such. This is what s hat is. So it's a very explicit way of describing s hat.
Are they all distinct components of S hat, or are they identified to each other? Because previously you talked about double cosets rather than just direct product of those cosets.
Forget about double cosets. This is the right way to think about it. The point is, okay, double cosets, so secretly, how does this relate to double cosets? This said here, it's like the product. We have a group action on this, on y hat, and we also have a group action on z hat. This group action permutes these components, y sub y, and it permutes the component z sub z. So this induces an action on, it induces a gamma action on this set. You can take the diagonal gamma action on this set. An element g just multiplies the first coordinate by g on the left and also the second coordinate by g on the left. Those double cosets correspond to the quotient of this by the gamma action, by the diagonal gamma action. So that's what that is. But this is much more, I mean, the way it was algebraically stated originally, it's not so visual, right? This is you can actually see what where those double cosets come from. They come from this diagonal action of gamma on this Cartesian product. So what's the goal? The goal is to pick a maximal essential set in Y, in Z, and in S. And we do it by first picking some sets in the hats. So we work with the hats first, and then we'll push everything to this diagram. That's the idea. The advantage of this diagram is that there is now a group action on each set, on each graph, or on each complex more generally. And all these maps, let's call this mu hat and this is nu hat. These maps are all leafages. Each of these maps is a leafage. That can be checked. So this map is a leafage, this map is a leafage, and then you check that these two maps also must be. Again, the reason pretty much is that this component is a subset of, can be viewed as a subset of this component. So it's an inclusion map, it's an injective map. From here to one of the components here. And the second map would be the injective map of this intersection into just one component, z sub z. So those are leakages. And we want to pick a set of edges in y hat and in z hat and in s hat consistently. We will do this using the order on the edges in here that we just defined. We know that these maps now preserve the order.
So are the orders gamma invariant when I said z hat y hat, or you don't care?
They are. That's what I just erased.
Gamma invariant.
It's an invariant order. Invariant because, again, depending on the way you define it, but in either case, it's a gamma invariant order. The reason is that, so once again, we identify the set of edges in x hat. We identified with gamma across some finite set, finite set. So the gamma action on here corresponds to the gamma action just on the left, on the first coordinate in here. That's gamma invariant. I mean, after you put the lexicographic order on it, it becomes gamma invariant.
The same thing for y hat, z hat, s hat.
Yeah, and then if you choose if you induce the order in here from x hat in the right way, then it becomes gamma invariant. And this map here preserves that order on each component. So let's take one of these, say y hat. So we have gamma action on y hat, and y hat has the set of edges in y hat has an order, right? Which is total on each component, or you can take it total on the whole set as well. So let sigma be one edge. It's an edge in y hat, and let's take E be a subset, some set of edges in y hat. So consider this situation. You pick some set of edges, and you also pick some edge. Let's assume they are different. So E is different from sigma. They are disjoint. We say that, so denote the set of edges in y hat less than sigma. This is just a notation. And this means that the set of edges which are less than sigma. It's the set of all tau in the edges of y hat, such that tau is strictly less than sigma. Where the strictly less with respect to the ordering that we have. So strictly less means it's at most sigma and not equal to sigma. So denote this, and then you say that sigma falls into E. And there is a reason for such terminology. We will see later on. It actually corresponds to certain analytic property. It corresponds to saying that like the boundary of a cell is included into certain Hilbert space. There is a way to restate this, which I will do later on in analytic terms. And that's where the terminology comes from. So say that sigma falls into E if one of the following things hold. And so here is the picture. You have sigma. You consider the, so let me draw it first. If there is a path connecting the endpoints of sigma, in such a way so that this path is in the set. So let's see, this is in E. Each edge in this path is required to be in this set of edges E. Or we have the following picture. Sigma, there is an edge. Again, there is not a path but a union of rays. Maybe infinite rays like this. Infinite rays. Infinite and injectively embedded into the graph. Again, those rays are in E. You call this, this is a finite vein. A finite vein. Vein, it's, I mean, that's something that you draw in a leaf, right? And this is an infinite vein, an infinite vein of, so for sigma, at sigma, at sigma. So in other words, it's either a finite path consisting of sets, consisting of edges in E, or it's a disjoint union of two injectively embedded infinite rays, consisting again of edges in E.
So x hat is a tree.
X hat is a tree. Yeah, you're right. I wanted to. Yeah, this never happens in a tree, right? But the point is that we actually don't have to assume that it's a tree. I mean, up to some point. Most of the argument works for general graphs, and one can make a general statement about graphs, not only about trees. That's why I'm presenting this general definition. Yeah, but yeah, if you are just interested in a tree, just think of this picture. Exactly. The point is that one can generalize a statement again for two arbitrary graphs. So it's a vein. And what is this E? Now we take this E to be this E is going to be the set, this set. So this is a general definition for any E, right? But now I'm taking E to be this set. So say that sigma in E an edge is order essential if order essential in y hat if sigma falls into that set, into the set of edges that are smaller than sigma. So it means that there is a vein. So let's unravel this. So it means that there is a vein, either finite or infinite, which consists of edges which are smaller than sigma. This is our blue. Maybe I should draw it like this. So
it says sigma is maximum on a geodesy, maximum on certain geodesy.
Maximum
is larger than any other edge.
That's right. Yeah, sigma is larger than any other edge on a certain infinite path.
Or just a circuit.
Or what?
Or a circuit.
Or a circuit. Yeah. So either this or this. Maximal. Yeah, sigma is a maximal edge either on some circle like this, a simple path, or on by infinite path. The first thing to observe is that this property really depends only on, so sigma was an edge in y hat, and the property of being order essential it depends not on y hat, but only on the component of y hat that contains sigma. So this property depends only on the leaf, right? So leaf meaning a component, connected component of y hat containing sigma. So one can draw that picture that you see on the first page, right? You can actually kind of draw the leaf here. I should have used green color, which I don't have here. So something like that. So this picture takes place in just one component. Then you immediately see that if sigma is order essential in say, I can give the same definition. Instead of y hat, take s hat, and the same definition for z hat. Right? So if sigma is order essential, if sigma is an edge in s hat, and it is order essential in s hat, then so what's the conclusion? I can apply this leafage map. Since it's a leafage, this component in which sigma lies maps injectively into y hat. Since it's injective, and since sigma was order essential, it means that sigma has a vein. Either this or this, either finite or infinite. So if sigma had a picture like this, you just map this picture down to y hat. That means that the image of sigma also will have a picture just like this. Moreover, since the leafage map preserves the order, this blue will remain blue. Right? It consists of all the edges that are smaller than sigma. So in the image, the same will hold. All those edges will be smaller than sigma. So the picture is completely preserved. So this property of being order essential is preserved under leafage maps like there. So then its image, let's say under mu of sigma is order essential in y hat. This property is preserved. That's one observation. The property of being order essential is preserved under leafages. The second observation is that we can consider the group action. We recall that gamma acts on y hat. And so if sigma is order essential in y hat, so it's an edge which is order essential in y hat, then you just pick some element g in gamma. Then what can we say about the image? We take sigma and translate it by the group element. Then take g dot sigma. Apply this group action to sigma. Again, what happens? Since sigma was order essential, there is a picture like this. There is a vein for a sigma. And then you apply the group element just to this whole picture. The group action preserves the order again. So it means that this whole picture will again be preserved by, if you shift it by some element g. So then g times sigma is also order essential. In y hat. So denote the bold font E y hat this set of order essential edges in y hat. What can we say about it? So this is a subset. This y hat is a subset of the set of all edges in y hat, right? So what can we say from here about this set? So if you take any element of this set and you apply any element of the group to it, the result stays in this set. So in other words, this subset of edges is invariant under the gamma action. The set of order essential edges is gamma invariant. Under this gamma action on y hat. Okay, since it's invariant, and maybe I should say, okay, and do the same thing. So similarly, we define the order inessential sets, the set of all order inessential edges in y hat. And order inessential is just the opposite of being order essential by definition. So an edge is called order inessential, in other words, if it does not have a vein consisting of smaller edges. This set, of course, so the set of all edges now is the disjoint union of the essential ones with the order essential ones with the order inessential ones. So we split the set of edges into two parts, and those two parts are both gamma invariant. Since this is gamma invariant, this is also gamma invariant. It's the complement. And we can do the same thing for, so define E z hat, E s hat. So the set of order essential edges in z hat, the set of order essential edges in s hat in exactly the same way, similarly. Okay, now we can draw a diagram. We can draw a diagram that is similar to that system. E s hat, E z hat, and E y hat. So I drew them that way. Now you look at this diagram here. This E s hat is part of this, and the other two terms are part of these two terms. If I take an order essential, if I take an element in here, that means it's an order essential edge in S hat, and map it, use that map mu to take the image of this edge in here. What's the outcome? The result is it's again an order essential edge. So that means that that map mu induces the map from here to here. There is an induced map. Similarly, in this direction also, that this map mu hat is just a restriction of mu hat and nu hat. This, the point is that they are well defined now. These maps make sense. Okay, so what would be the next step? Then, now recall that this is invariant under gamma, this is invariant under gamma, this is invariant under gamma. And these maps, the diagonal maps in the system, say going from y hat to y, or from s hat to s. Those maps were the quotients by the group action. Those diagonal maps in the system of complexes that I drew, those maps were the quotient maps by the group action. So we do exactly the same thing here. It's just a restriction of that diagram. Since this is a gamma invariant set, we can take the quotient. So denote the bold font EY to be the quotient of EY hat. So this is a set of edges which is invariant under gamma. Just consider the set of all orbits, right? So each orbit you can view just as one edge. Identify all the edges in the orbit. This is the result. But of course, this is a subset of what? It's a subset of edges in Y. It's a subset in Y, if you like. Right? If you view Y as formally as a disjoint union of edges and vertices. So it's a subset of edges in the graph Y. And it's a finite graph. It's a finite quotient. So I can draw it here similarly to the system of complexes that I drew before. So I can put it here. EY, and this is the map. This is the quotient map by the group action. So each element is replaced with the orbit of this element. Similarly, we can do this for E, ES, and EZ. Right. These diagonal maps are the quotients by the group action. Now you recall that mu hat is invariant. It's gamma equivariant. It commutes with the group action. Since it commutes with the group action, it means that each gamma orbit in this set goes to a gamma orbit in here. And that means there is an induced map on the quotient. And here also, there is an induced map on the quotient. So this whole picture is exactly, looks very much like the system of complexes, right? This is part of the system of complexes. Okay, now look at these two arrows. So recall, this is part of this diagram, S, Y, S, Z, Y, X, right? Recall that this diagram was a fiber product diagram. And we need to recall the definition of the fiber product. What's the definition of S? If these were graphs, S is going to be a graph. The vertices of S are exactly the pairs of vertices in here. The edges in S are exactly the pairs of edges in Y and Z. So in particular, S, so the set of edges in S can be viewed as a subset of the set of edges in Y cross the set of edges in Z. Right? Just by definition, an edge in S is a pair of edges. Not the whole Cartesian product, but only those pairs which map to the same edge in here. But it's a subset in here. But now instead of this fiber product, you look just on these two maps. These two maps are restricted versions of those. And that means that the bold font E is a subset, can be viewed, maybe I should say formally. Maybe I should say formally, this is can be included. There is an injective map. And this set is just, this map here is just a restriction of this map. This can be included into EY cross EZ, where I use this bold font. So these are the edges that come from other essential edges in Y hat, in Z hat and in S hat respectively. So this map includes into the Cartesian product. If you know the cardinality of these two maps, of these two sets, what can you say about the cardinality of this set? So then the obvious implication is that the number of elements in ES is at most the number of elements in EY times the number of elements in EZ, right? Just because this is a can be viewed as a subset of the Cartesian product. These are finite sets. So this is also a finite set, and this inequality holds. So you see that this looks very similar to the Hahn-Neumann conjecture that we actually want to prove. The Hahn-Neumann conjecture said something about S, Z, and Y, right? I mean, when you restate it in terms of graphs. The statement was that the reduced rank of S should be at most the reduced rank of Y times the reduced rank of Z. That's the goal. But this is what we have now. It only remains to show that each of these numbers actually is the corresponding reduced rank. So we want to show that the reduced rank of Y is the same as the number of elements in this quotient. Right, that's the goal. If we prove this, we are done. So the same proof will work for Z and S. But how do you prove this? In order to prove that, it suffices to show that this set here, so it suffices to show that this is a set of edges in Y. It suffices to show that this set is a maximal essential set in Y. The set in the graph Y. If you prove this, then we are done. How do you prove that it's maximal essential? So there are two conditions here. First you show that it's essential, and then you show that it's maximal. Why is this essential? So prove that Y is essential. Is an essential set in Y. So let's recall the definition. What does it mean for a set of edges to be essential? So we need to show that if you start with the graph Y and you remove all these edges, then the reduced rank decreases exactly by what? Exactly by the number of edges that you removed. So in other words, if you remove them one by one, you pick one edge here, remove it from Y. You take another edge here, remove it from Y. You want to show that at each step you decrease the reduced rank exactly by one. This is what essential means. Let's see how we can prove this. We need to unravel the definition of this. This was the quotient of the set of other essential edges. So this is the picture. Take this E sub Y, EY. So pick some element, take some sigma. I'm taking just one element in this set. So it's a graph. But it comes from EY hat, right? It's the quotient map, the quotient by the group action. So in the what's the preimage of this sigma under this quotient map? The preimage is the whole orbit of edges. So let's draw them like this. So we have an orbit of edges. Maybe let me call it sigma prime or something. And this is sigma. So pick any edge in the orbit of the preimage. What is sigma? Sigma is an element of this set by definition, right? It's in the preimage because this set was defined as the quotient of this. So in particular, sigma is order essential in Y hat. Since sigma is order essential in Y hat, it means that it has a vein consisting of smaller edges. So it would be a vein like this. right? Where each vein, where this vein consists of edges that are smaller than sigma. Okay, so but there is a problem here, right? It might consist of edges that are smaller than sigma, but some of these edges here might also map to the same sigma prime, and then you cannot really run the argument. This vein might also map. Some edges in this vein might map on the same sigma prime, and that's pretty much the main problem. Was in kind of trying to prove the Hahn-Neumann conjecture using, finite graphs, because you run into these kind of problems. So we need a better way of doing this, and this leads us to the notion which is called the deep fall property. So before we prove this, we need another property. We need a stronger condition. So deep fall property for graphs. Start with a graph y hat. And we consider a group action, free group action on y hat, and we can define order essential edges. I mean, we assume that the edges are ordered, and the ordering is preserved by the group action, just as before. The deep fall property says that. So in a graph y hat. As before, meaning it's a graph with a group action and the edges are ordered, and the order is preserved under the group action. So in a graph like this, if sigma, you take an edge in y hat, if sigma falls into the set of all smaller edges, right? This means that sigma is order essential, right? This is just another way of saying sigma is order essential. Then sigma also falls into a smaller set, namely the set of all order inessential edges that are smaller than sigma. The definition of this, it means the set of all edges which are here and which are smaller than sigma, the same definition as before. So if sigma falls here, then it falls into the smaller set. Equivalently saying this, if sigma has a vein consisting of smaller edges, then sigma also must have a vein consisting of edges which are order inessential and smaller than sigma. So it's a stronger condition, right? This is a weaker condition, this is a stronger condition. How do you prove this? So this is roughly the idea. You start with sigma, and we can assume that everything is countable, of course. Actually, I mean, this whole argument can work when the graphs are not countable. But you assume that the group by the action by the group is, you assume that the graphs are locally finite. You assume that the action is co-compact. So we could just restrict our attention to just one component. So the total graph y hat doesn't have to be countable, say. But if you restrict it to just one component, everything becomes countable. So it's not an issue here. Well, I just wanted to say that we could prove the same thing for uncountable graphs. So sigma falls. So let's draw it. This is how. This is just a notation. Sigma falls into E less than sigma. Sigma falls here. It means sigma has a vein here. If it has a vein, so here's the vein. It's a vein consisting of the edges that are smaller than sigma. But some of those edges might be essential or non-essential, right? And that's the problem. We want all of those edges in the vein to be inessential, order inessential. But some of them might be essential. So what's rough? First, let me present the rough idea. The rough idea is not going to work, but at least it gives you an idea how to proceed. So the rough idea is the following. You take another sigma, let's call it sigma 1, say. And on this vein, you pick an edge on this vein such that sigma 1 is order essential. It means that it does not lie in this set. So here is the formal, maybe I should say formally. So enumerate the edges in the order essential edges in y hat. So just enumerate as sigma 1, sigma 2, and so on. It's a countable set. So I'm taking just suppose sigma 1 lies on this vein. Then I want to remove it. I want to find another vein which would not contain sigma 1. So the idea is to to keep removing those edges until we are left only with the order inessential ones. Okay, let's try to remove sigma 1. Sigma 1 is order essential, and that means that...
Do we enumerate the whole essential, not the...
Yeah, the whole thing. I mean, you just take the first one, which occurs on a vein. Right? If it does not occur on a vein, then you don't do anything. If it occurs on a vein, then sigma 1 is order essential. And that means it has a vein. Like this. And then it means that instead of the sigma 1, we can replace it with the vein. So we can erase sigma 1 and draw the vein instead. Of course, those veins, they in general, if the graph is not a tree, they in general might somehow intersect. The picture might be more complicated here for a general graph. But still it works. You remove this edge and you replace it with a vein. What is left is kind of a bunch of, here is a ray, here is a ray, a bunch of rays. And here is part of the ray, an interval. But you can take pieces of those and make a vein for sigma which does not pass through sigma 1. So here is the one, right? This is one part. Then this interval composed, concatenated with this infinite ray. Yeah.
Do we have to guarantee that sigma 1 is strictless and sigma is...
Yeah, we need to guarantee, but that is guaranteed because that's how I chose those veins here. Sigma was order essential. It means that it had a vein consisting of smaller edges. So if sigma 1 occurs on this vein, it must be smaller. So it's automatically smaller. But you're right. I mean, there is a problem. One needs to be careful here to make this work. This is just an idea which does not work. I mean, one needs to write a formal proof to really make it work. But that's a rough idea. Remove sigma 1, so we got a vein which misses sigma 1. We got a vein at sigma which misses sigma 1. So find a vein. There is a vein at sigma that misses sigma 1. Then you take sigma 2. Follow the list. If sigma 2 is away from this, we don't care. So if sigma 2 happens to be on this vein again, maybe it's somewhere here. This is sigma 2. Then you hope to run the same procedure, right? So sigma 2 is again order essential, so it has a vane. And we remove sigma 2 and replace it with its vane. And out of those pieces construct a vane at sigma which misses both sigma 1 and sigma 2. And I cheated everyone here. It doesn't work. So the claim is that there is a vane at sigma that misses both sigma 1 and sigma 2. So where was the cheating?
Does it really converge?
What?
Does it really converge?
I'm not talking about convergence, just two edges so far. Yeah, later on we will have to converge, but so far just two edges. Even at this point already, the argument doesn't actually work exactly as we want. The problem is that sigma 2 actually might be bigger than sigma 1. And it might happen that this sigma 2 actually is somewhere here. Sigma 2 is above sigma 1. It's bigger. And okay, if you try to draw a vane here, you drew a vane, but this vane that you drew, it might happen to pass through sigma 1. And if that's the case, okay, you erased sigma 2, you replaced it with a vane, but this new vane contains sigma 1 now. You cannot guarantee that the result misses the edge, right? So, but still, we want this idea to work. So the idea roughly is to take one by one edges and replace them with vanes. We just need to make sure that we do it in a consistent way. So what's the right way to do it? It's still possible to do. So the right proof, the correct proof. So fix any number n. And consider, so as before, we enumerate all the other essential edges as before and consider only the first n of them, sigma 1 up to sigma n. The problem there was that sigma 2 might be bigger than sigma 1. That was the trouble. But now we avoid that problem by ordering this finite set. There is a, so use the order. Use the order on the set of edges. So relabel this set as tau 1 up to tau n, such that tau 1 is bigger than tau 2 is bigger than, and so on, tau n. So you just relabel, you re-enumerate this finite set. It's possible to do for the finite set. It's not possible to re-enumerate this infinite set, but we can do it with finite sets. And now you run exactly the same argument, but with taus instead of sigmas. So tau 1, we have a, so once again, we have a sigma and it has a vane consisting of smaller edges. So if tau 1 occurs on the vane for sigma, and tau 1 is again order essential, so draw the vane for tau 1 and then replace tau 1 with the vane. with its vein. Its vein that consists of smaller edges, smaller than tau 1. Get a vein at sigma that misses tau 1. And then continue. Tau 2 is smaller. Do the same for tau 2, tau 3, and so on. So you take, if tau 2 happens to occur at in this vein, then tau 2 also has a vein, so you replace tau 2 with the vein. And since they are ordered like this, we can do it consistently, and what you did at the next step does not affect what you did at the previous step. So the result is a vein at sigma that misses all of them, misses tau 1 up to tau n. And that means it misses sigma 1 up to sigma n. That's the same set. We just did it in a different order. This is true for, this works for each n. So for each n, there exists a vein at sigma which misses all the edges from sigma 1 to sigma n. And now we take a limit, right? What does it mean? It means that you can choose a subsequence. The fact is that this graph is locally finite. It's possible to choose a subsequence. There is a subsequence of these veins, of such veins, that pointwise converges to some vein. That just at each edge it stabilizes after some point. So what's roughly the idea? You have one vein, you have another vein, you have many veins here. For each number n, you have a vein. And you want to have take a limit. But since it's locally finite, it means that out of those infinitely many veins, most of them will go through some edge here. There is a subsequence of this finite, infinite sequence, such that that subsequence of veins goes through just one edge here. But then from this edge, there are only finitely many edges branching out. Again, you pick a subsequence, so there is exactly one edge. There is at least one edge through which infinitely many veins pass, right? And you keep choosing those edges like that. So you end up either with the closed vein, in the case like of a general graph, or you end up with an infinite vein, either finite vein or infinite vein. But at the end, you will get a limit. There is a subsequence of such veins that converges pointwise. More precisely, it stabilizes at each edge eventually. Converges to a vein at sigma. But since in a sequence those veins missed bigger and bigger subsets of this, then the limiting vein will miss this whole set. This vein misses all the edges in the essential part of y hat. So we constructed a vein at sigma which misses this. It means that this vein consists of the edges that are order inessential. This proves the deep fall property for graphs. So if there is a vein in this set, then there is a vein in this set. for sigma. So going back to the proof, you remember we wanted to show that this set is essential in Y. This set by definition was the quotient of this set, of the set of other essential edges in Y hat. So we pick any edge sigma prime and consider the whole preimage of sigma prime. That is an orbit of edges. Since sigma was order essential, it means that there is a vein. But now, additionally, I can assume that this, what is blue here, consists only of order inessential edges. So maybe this is in the order inessential edges of Y hat. Okay, so what happened here then? So we split the edges into essential ones and the inessential ones. So the inessential ones are in blue. Now consider this vein. And what's the image of this vein? So if it's an infinite vein, so now I'm assuming that it is indeed a I'm assuming that we are in a tree now. So I'm assuming that the vein is infinite. What's the image of this vein in here? Since it's an infinite ray, but this Y here is a finite graph. So this vein must wrap around. The picture should be like this. It must be something like that. Maybe with a few, but there is at least one loop in the image. Right? It does not backtrack. Right? There is no backtracking here. We assumed from the beginning that it's an injective embedding of a ray into the graph. So there is no backtracking, and that means it must make a loop. So in other words, I'm assuming here that this is a covering space. Y hat is a covering of Y. The reason is that there is a free action by a group on Y hat, and the quotient is this. So it's a covering. And since it's a covering, if there is no backtracking here, it means that there is no backtracking here as well. This infinite ray must map to a loop, at least one loop in the image. Similarly, on this side, it must map to at least one loop on the left as well. And if you have one loop on the left and one loop on the right, what happens if you remove this sigma prime from the graph? It means that sigma prime is an essential edge. It would be not essential if the remaining graph was a flower or a tree. But this is not the case, right? Wait. No. It could be a flower, yeah. The point is, so the condition is the following. So you take this edge, and you require that after removing this edge, the component containing the left point must contain at least one loop. And you also require that the component containing the right endpoint also has at least one loop. If that's the case, then removing this edge strictly decreases the reduced rank.
Those loop on the left and right can go same.
They can be the same thing.
Right.
Exactly. Still, if that's the same thing, then
then you have
if that's the same thing, if that's the same thing that you have an edge like this, still it does decrease the reduced rank. Yeah, they could be the same. Okay, that shows that sigma prime is order essential. Is essential in this finite graph. I need some chalk. Okay, but there might be some other edge, right? Which is so we remove sigma prime. It decreases the reduced rank. So take another edge which is still in this set. Call it, I don't know, sigma double prime. sigma double prime, by definition, it comes from this set. This is why I drew it in white. White means it's in the image of this set. And for sigma double prime, we have the same picture. There is a preimage here, and again, you can take an arbitrary sigma here. And again, you have a vein here. That vein, by the deep-fall property, consists only of other inessential edges. And that vein, since it's infinite, must map to a picture like this. So there must be at least one loop on the left of sigma double prime. There must be at least one loop on the right of sigma double prime. Right? And now you see that still, even after removing sigma prime, if at the next step you remove sigma 2, you still further decrease the reduced rank. Again, because of the same property here. There is at least one loop on the left and there is at least one loop on the right.
So you're using the fact that there are circles consisting of image of inessential edges. Is that right?
That's right, yeah.
So what if...
And inessential, it means that it's disjoint from sigma prime.
So what if... so it cannot happen that like the left infinity disc and right infinity disc forms a circle?
Yeah, then it doesn't work, yeah. Let's see. Let's see. It does not work because, I mean, it might be like this. Removing this edge,
that's not what you want.
It might be that you just map this picture downstairs, exactly in the same way. The same picture downstairs. Right? And yeah, this would not be enough. This edge would not be.
So that
would not be essential in the quotient.
So that doesn't happen in this case. Like closing a circle on the downstairs doesn't happen.
It might happen, but we don't care. All we care is that the image of this part, left part of the vein, makes a circle.
Oh, I see.
And the image of the right part of the vein also makes a circle. So this blue is disjoint from white. And therefore, if I remove this, it means that this sigma double prime has two circles on both sides. And those two circles miss sigma prime. So we can, after removing sigma prime, we can also remove sigma double prime and then continue in exactly the same way. The point is that blue is disjoint from white. So we use the deep fall property to show that removing the edges from this set one by one strictly decreases the reduced rank by 1. So this proves that the quotient of other essential edges is essential. It's an essential set. The next thing would be to show what? We are left with showing that this set is maximal. Let me remind you what maximal is, and maybe I'll continue next time. Maximal means that if you start with the graph y, and then you removed all the edges in this set from y, then the result should be what? Yeah, it should be a garden, equivalently saying the reduced rank of the result should be 0. Yeah. So we want to make sure that after we removed all these edges from y, the result is a garden. That we'll do next time, or you might try to do it meanwhile before the next week. Thank you.